Lesson 11, demo number 2. There is another test that can sometimes be used in lieu of the first derivative test to determine if a critical number is a max or a min, and it may be easier to apply. Analyze the concavity at the relative extrema pictured below. So I'm going to put a dot at the relative extreme points. Each graph has one. And we're going to figure out what's happening with the concavity at each of these 3 blue points. So for the left-hand graph, this function here is concave up everywhere. And it happens that the blue point is a relative minimum. In the middle graph, the whole graph is concave down everywhere. So in particular, at that blue point, the graph is concave down. And it turns out that concave down gave us a maximum. In this next picture, the graph on the far right here is concave down on both sides, but the concavity isn't defined at the blue point, because that blue point is a cusp or a corner point. And we know that f prime doesn't exist at corner points. And so if f prime doesn't exist, then f double prime also doesn't exist. So I mean, it happens that it was a minimum point in this case, but you could easily flip that graph over, make it a maximum, but still we don't have any information about the second derivative there. Okay, so number 2, the second derivative test. If f prime of x sub 0 equals 0, so here we're thinking of x sub 0 as being the x coordinate of the maximum or minimum point that we're talking about. So if f prime of x sub 0 equals 0, which is our flat tangent line, and f double prime is positive, which we now know means concave up, so that's this. So f double prime, not anywhere, but at the particular value of x that we're focused our attention on. So the f double prime of this guy is some positive number. Then f must have a, well, what was this? Was it a min or a max? In this case, it was a min. And this is true all the time. Is that if you're sitting at one of these critical points and your second derivative is positive at that critical point, then you are sitting at a relative min. Part B, if f prime of x0 is 0 and f double prime of x0 is negative, that's the middle picture here, concave down, then f must have, just like that middle picture, a relative max. If f prime of x sub 0 is undefined, like in the far right picture, then this test is inconclusive. You can't say whether you have a min or max. You really can't say anything. Try the first derivative test. Part D, if f prime of x is 0 and f double prime of x is also 0, so that means we're not in either of these cases. F double prime isn't positive or negative. But if it's 0, then again, the test is inconclusive, so use the first derivative test. And it says the second derivative test automatically does not apply to points where the derivative is not defined. So let's see this second derivative test in action. So number 3. Let's find the critical numbers and then use both the first and second derivative tests to decide whether they are local maxes or mins. Okay, so first the old stuff. To find the critical points, we take the derivative and set it equal to 0. Or we figure out where the derivative is undefined, but this derivative is defined everywhere, so it's just about setting it equal to 0. So move the 27 over. Divide by 3, take the square root of both sides. Don't forget the plus or minus. Okay, so we know that we have 2 critical points, x equals 3 and x equals negative 3. And the question is, are they both mins? Are they both maxes? Is it one of each? Maybe they're not mins or maxes. And we're going to use the old first derivative test to answer that question, min or max or neither. So the old test says you put your 2 numbers on your number line. Notice that this number line is already labeled with the function that these 2 values of x came from. Plus minus 3 came directly from taking the second derivative and making it 0. And then we're going to pick points in each of the 3 intervals and plug into this derivative function. So if I put 100, I'm out here in the far right, 100 there for x, 100 squared is very big and positive, triple it, big and positive, subtract 27, slightly less big, but still very much positive. Pick a number between negative 3 and 3, for example, 0. 0 here for x gives me nothing minus 27. That's negative 27, so I've got a negative there. And then finally picking a number out here, like negative 100. If I take negative 100 and square it, it becomes positive. It's the same is positive 100 squared. So very big positive, subtract 27, still positive, so plus there. And so in my mind, I know because the first derivative is positive, the original function must have been going up, increasing that whole time. Then it must have been decreasing because f prime was negative, and then the original function must have been increasing again because f prime was positive. And so -3, is it a max, a min, or a neither? Well, just looking at this very rudimentary graph, it is a max at -3. And how about a +3? Right down here we have a min. So max at -3, min at +3. We'll fill in the blanks with these familiar justification sentences at the end of the first derivative test. Since f prime goes from, let's say the first one, the -3 one, goes from positive to negative at x equals -3. So to the left of -3, f prime is positive. Just to the right of -3, f prime is negative. F must have a local, I said max, at x equals the same -3. And then focusing our attention on x equals 3, f prime again goes from, now it goes from negative to the left to positive to the right at x equals 3. F must have a local min at the same x equals 3. Okay, so that's the first derivative test, all old. So now what we're going to do is talk about the second derivative test. And the idea is we're using it instead of this. We still need to do the critical point calculations like we did up above. So we need to figure out where the derivative is 0. And we saw it happens at 3 and -3. And so now the question is, which one of those is a max, which is a min? Maybe it's 2 of one, none of the other. So it's answering exactly the same question, but in a different way. So here we go. Second derivative test clearly involves finding the second derivative. So let's find the second derivative. I can see the f prime right there at the top of the screen. So the second derivative of that is 6x, and then the -27 goes away. And what we are going to do is plug our two critical points into the second derivative. So -3 and 3. And so if I plug -3 in for x in the 6x function, I just get 6 times -3, or -18. Let's keep going on this line. Since f prime of -3 is -18, sorry, that is not what I meant. Since f prime of -3 is 0, that was the critical pointness of -3, and f double prime of -3 is -18, which is less than 0. And we just have to figure out what's happening at x equals -3. Let's think about our conclusion. In my mind, I have only two possibilities. I have a concave up possibility and a concave down possibility. And I'm just trying to decide which one I'm in. Because whether you're concave up or down completely determines whether you're sitting at a min, like the left-hand blue parabola thing, or a max, like the right. So in our case, we saw that f double prime was a negative number. That means concave down. That means this one. And if you're at a special point on a concave down curve, then you must be at a maximum. So f has a local maximum at x equals -3. And notice that's exactly the same conclusion that we came to up here. Local max at -3. Still a local max at -3, but a wholly different way to think about it. We didn't do a sign test down below. We analyzed the sign of f double prime. Okay, let's do the same thing now, but for 3. So in this case, when we plug 3 into the f double prime function, that's 6 times 3, or 18. F prime of 3 was 0 because it was a critical point, and f double prime of 3 is positive 18, so bigger than 0. And so thinking about my two blue parabola looking things here, f double prime is bigger than 0. That means concave up. That means in this one, that means the green point is a min. F has a local min at x equals 3. So that is the second derivative test. It gives you exactly the same conclusions as the first derivative test, just a different way to answer the same kind of question. In both cases, you start by finding the critical points, and then how you decide whether those critical points are maxes or mins or neither varies, whether whether you use the first derivative test or the second derivative test. But the answers will clearly be the same at the end of the day. So that is the end of demo number 2. So give a shot at activities number 2.